Hey everyone, welcome back. This video is about wire sizing. So I've either got some previous videos or some upcoming and future videos that where I talk about wiring, and didn't want to stop and explain wire sizing every time. I might do that occasionally, but so I wanted to just create a dedicated video, talking about the basics of how you choose how thick of a wire to use. So there's two situations you got to consider. You've got a power source, you got a fuse block or distribution block, and then you've got a load over here. The first situation is when the negative or one of the outgoing or return path is going through chassis. And the second is when that return path or negative is not going through chassis. And the difference is when we get to the actual wire sizing example, it depends on how long the wire run is. In the case where we're grounding to chassis, we assume that chassis is a very, very large diameter wire, and it usually is. There's a lot of metal and it's almost got zero resistance. So we kind of assume this is not contributing to the overall resistance of the circuit, but this is. On the other hand, there are good reasons not to run the return path through chassis. So in that case, we've got resistance here and resistance here. And so, we'll measure the length of the run from power source to load, and then we'll double that length. And that's the length we'll use when we do the wire sizing calculations. If you're an engineer or the basics of Ohm's law, this ampacity table might be better for you. Gives you a little bit more flexibility in doing some of the calculations. What you see here is an ampacity chart for milspec wires, so stuff that you'd find in like airplanes, military vehicles, and you'll see a row for every gauge. So here it's 24 to double aught, and the column you're looking for is this resistance in ohms per 1,000 feet. I think in metric it's resistance in ohms per maybe 100 meters, I think, not 1,000 meters. Resistance is going down the larger the wire is getting. If you know Ohm's law, this gives you more flexibility, but then you got to decide, okay, how much voltage drop is acceptable in order to use Ohm's law. So it's voltage equals current times resistance. So you need to know how much voltage you're willing to accept dropping across the run. There are pre-calculated tables that take Ohm's law into account. One of those tables comes from the FAA for aircraft. So the FAA published these things called advisory circulars. This one's acceptable methods and techniques and practices for aircraft inspection and repair. The AC number is 43131B. And some of these advisory circulars are like 1 page long. This one is like 1.5 inches thick printed book. It's pretty extensive. Back in chapter 11, page 30, they've got a chart all made out for systems with different voltage levels. This is the 12 volt on the far right. They've specified no more than a 0.5 volt drop, and then this is the length of the run between power source and load if you're grounding through chassis, if you're not grounding through chassis, running all the way back to negative on the source, you got to double that number. So if you got a 10-foot run, you got to double it if you're not grounding through chassis. So, and then these are lines of constant current draw or amp draw. And then I'll use one of their examples here. So say you've got a total wire run of 12 feet. You kind of go over to, let's say you need to pull 20 amps. So 12 feet, 20 amps, you drop down, it says, hey, I need 12 gauge wire. And if you fall in the middle, then you go up a wire size. So if you fall in the middle of 10 and 8, you go to 8 because that's the larger wire, it's safer. This is for continuous flow, but sometimes you've got a circuit where, a branch circuit where you've only got, say, intermittent or peak. So you might be like 1 amp just sitting there continuous, but it might peak to say 10 amps briefly. The FAA doesn't care about, voltage drop on the load so much as where that energy is going, and it's going into the wire as heat, and they're concerned about things catching on fire. So for brief periods, they're willing to let you pull more current. So in that previous example, say the wire run was 12 feet again, and you go over to the 20 amp line, which is right there, and you drop down, and yeah, we're at, what's that, 15 gauge? Yeah, so nobody sells 15 gauge except maybe the Chinese, and you don't want to buy that stuff. So you go to the next largest wire size, which is 14. So in the previous example, with a continuous load of 20 amps, you had to go to 12 gauge. If the circuit's only intermittently loaded to 20, you can get away with 14 gauge. Hey everyone, future me here. After I shot the video, I realized that I missed something very important about the ampacity charts or tables based off of the ampacity charts. Best case, you're going to find an ampacity chart for the specific wire that you bought. Kind of, next acceptable level is, find an ampacity chart for the same type of wire. So, if you're using milspec wire, it's pretty similar to marine grade wire. They're both tin copper, and they're going to have very similar ampacity characteristics. But if you use bare copper, I bet that the ampacity characteristics are going to be different enough where they might change some of the answers. So, just make sure you're using ampacity charts or tables from the manufacturer, or at least for a very similar wire. All right. So this is mostly important in aviation, not so much elsewhere. But a lot of times you'll have wires in a bundle, and because the wires running on the inside of the bundle are insulated by the wires on the outside, it can't get rid of heat as well. So you've got to derate the bundle. You don't really put less current through it because the loads still need the current they need. What you're doing is using this factor to adjust the wire gauge for that necessary current. They've got different curves for bundle loading percentage and number of wires in a bundle, and then you get your correction factor, and your wire gauge is basically going up by the reciprocal of this. And then definitely, for aviation is derating factors because of altitude. So, as you go higher, air gets thinner, which means it has less ability to transfer heat out of the wire or wire bundle. So, at 10,000 feet, which is probably where most, road vehicles are topping out, you're really only doing a 5% derating. But like, say, an airplane flying at 40,000 feet, yeah, you got to derate the wire by 15%. So one more thing, and I got to flip back to the beginning. Yeah, so let's just use this one. So everything I explained was either for just the load side or the supply side of the fuse block. But someone might ask, and I did myself, well, I mean, if you're pulling current here, and another branch circuit's pulling current here, I mean, that second branch circuit is dropping the voltage on that supply more than just this first load would be. So you have to kind of consider all the loads, technically speaking, when you're doing this. And I created a spreadsheet that did that for one of my setups in a camper. And what I discovered was if you can mostly treat the load side and the supply side separately. There was some corner cases, some oddballs where like if I decrease the size of the supply side by like one gauge, so like 6 gauge to 8 gauge, the size of this wire might have to go up a little bit to the next larger wire. But by and large, you can just treat the supply side and the load side separately and get away with it. If anybody's interested, what I'll do is put that spreadsheet with the derivations as a link to like my Google Drive. Just let me know in the comments. Hey, future me again. Sorry, I just wanted to do a quick follow-up to what I'm doing to size the wires going to a fuse or distribution block. So generally what I do is just look at the rating of the fuse block or distribution block, and I look at the length of the wire run, and I just size that supply side to meet the rating of the block. Sometimes that's overdoing it, and I'm paying more because I'm using larger wire, but generally that's what I do. Like on these 100 amp fuse blocks or distribution blocks, typically it always ends up being 6 gauge wire if you're curious. Maybe if you get an especially long run, it might go to 4 or 2, but 6 gauge usually works for these for reasonable wire runs. And the nice thing about 6 gauge wire is the Blue Sea fuse blocks, you can fit them in through the side to get to the terminal studs. If you go up to 4 or larger wire, you have to kind of come in from the top, and that may not look as clean. But that's how I do it. I just kind of like usually look at the fuse rating of the block and then just size the wire to that. I get it. Money can be an issue, so you do you. Just make sure you fuse for the right size wire. You're not fusing for the current that's going through the wire. You're fusing for the size of the wire. So just make sure you're fusing for 100 amps in the case I just described, or fusing for whatever you decide to. I think that's it for wire sizing. Just remember, am I grounding through chassis, or am I running a wire all the way back to the supply side negative, because it does change the answer quite a bit. And if you get it wrong, your wires are at risk of melting. So because you're going to select the wrong fuse size, I think. For the wire, you're going to go down that wrong road, and the fuse always protects the wire, not the load. So that's how you get yourself into trouble. All right, so I think that's really it this time. All right, thanks everyone.